Okay, let's see how some exponential equations can actually be sort of useful. So say we're doing science and we have 100 milligrams of something that doubles every year. I'm going to go ahead and try to write a model for how much I'd have left after t years. So I'm going to use t, my variable t, for the number of years. And I'm going to write a model for how much I have left. So let's just kind of work this out. After 1 year, I would have, so 1 year, so t I guess equals 1. I would have 100 times 2, because it doubled, so times 2. After 2 years, I would have 100 times 2 times 2, because it doubled again, so times 2 again. After 3 years, I would have 100 times 2 times 2 times 2, because it tripled. Oh no, sorry, it doubled again, so times another 2. So if I wrote this out, this would be 100 times 2. This would be 100 times 2 squared. This would equal 100 times 2 cubed. And so hopefully you see, as my t gets to be a different year, that's what changes with my exponent. My exponent is a different year. So my model would be the amount I would have would a of t, I'm just using a for amount, would equal 100, my base amount, times 2, because it's doubling, to the t, because after 1 year it was times 2 to the 1, after 2 years it was 2 squared, after 3 years it was 2 cubed. So what would change if it tripled? If it tripled, I would still need an a of t. My base amount, my starting amount, was still 100. This time, though, it's not doubling, so it's not going to be times 2. It's tripling, so it's going to be times 3. Still to the t, because every year it would be times 3 times 3 times 3 in the second year, so times 3 squared, times 3 times 3 times 3 in the third year, so times 3 cubed. So just 3. Okay, what if it doubled every 3 years? So I'd still have a of t. Base amount is still 100. It's back to doubling, so I'm going to go back to 2. And it's not doubling every year, so in 1 year, it's not going to actually double. It's not actually even going to double in 2 years. It takes 3 years to actually get to that first 2, to that first doubling. So I'm going to say t divided by 3, because when that hit 3, my t hits 3 years, this would just be a 2. When my t hits 6, so another 3 years, that would then be 2 squared. So I'm going to have it like that. So we're going to set up just a standard model. We're going to call it a to the t. It's going to equal our initial amount. So a naught. Naught is the little O there, and it usually stands for initial. A naught times whatever's happening. If it's doubling, it's 2. If it's tripling, it's 3. If it's half-life, which we're going to talk about in a minute, then it's 1/2. So we're just going to say 2. We're going to keep that doubling for a minute. To the t over a. So that would be the amount of years it takes to actually double. And we can use this when solving different exponential problems.